We're on. Okay. All right, first of all, I have an announcement. I don't understand this. It says, please announce during your class that Feeds Media Center students should pick up their CDs if they have not done so. Of course, if they're watching this, then they must have picked them up, so I don't understand this. But it says announce it in class, so I did it. Otherwise, let's see, the midterm exam will be next Thursday. It'll be here. Open book, open notes, and I gave you a sample exam, which I'll discuss later on today. And I also want to go over the homework today, homework 0, which I just handed back. If you have any questions about the solution or problem in general, ask them in class. But if you have specific questions about your grade, then ask it after class. Let's see, I got your Lazon, Mitchell, Alvarez, Mueller, Barber, Bartholomew, Lanoff. Okay, so first let me do homework 0. Because I did most of it in class already. So the only thing that I hadn't done was basically it was a convolution for case number 1. But let me review this in detail. I would say that most people don't understand this. Because it always happens that way, so I don't know what the problem is. I think that for some reason that the freshman calculus course just doesn't get through, or the wrong things are emphasized. I don't know what the reason is. But it's really important to know this kind of stuff, because remember, you're going to get a degree in computer science or computer engineering from College of Engineering, a state university. And so this is basic stuff. I mean, every scientist and engineer should know freshman calculus. And you don't have to memorize things. You're supposed to understand it, so that if you get a problem that you don't know how to do immediately, which would be most problems if you're not taking the course at the time, you should be able to figure it out. I mean, scientists and engineers have to figure things out. Nobody's ever going to ask you questions that you look up in the back of the book. Those are just stupid. It might be good for learning purposes, but eventually, any question worth asking is one that is not exactly a textbook problem. So the basic idea is you learn these principles, and then you use them to answer all questions, not just the ones that you happen to have seen examples of. So if you figure in a course like this, I gave you what, as I'll show you, is really the simplest thing you can come up with, and you have 3 weeks to do it, and you can ask anybody in the world and get any help you want. Everybody should get 100% on this, but almost nobody got the convolution problem right. Also, I noticed that very few people use calculators. I mean, you're computer scientists and computer engineers. All you got to do to calculate these integrals is press a button. And so some people didn't do it. Some people wrote out lots of stuff by hand, which might have led to the right answer, but was unnecessary. So let me go through the whole thing. Also, one thing I got to stress, I want to say this, probably mention it again, is that everything has to be internally consistent. Otherwise, that's cheating. Look at the syllabus. At the bottom, there's a note. And the note says that if you do things like run a simulation, and then you put the answers in the table that are different from what the program gave you, that's cheating. If you put in the wrong answer, that's okay. It's wrong. Now, in a case like this, there are graphs and there are formulas. And the graphs and the formulas come from each other. That is, okay, put you in here. So you're supposed to... Thanks. What was that? Okay. So, for example, if you have a formula and it gives you a certain curve, and then you draw the graph that's different because you know that the answer is supposed to be a triangle or a square, then that's cheating. You're not supposed to do that. If you don't know how to derive the formula, well, then just say so. That's only worth a few points. But it's deceptive to draw a graph as if you calculated it when in fact you didn't. So I took off lots of points for that, and in the future that'll be worse because you're being warned now. Don't do that. If you don't know how to do something, just say so or leave it blank. But don't make up answers or copy partial answers. If you're going to copy, be smart and copy the whole thing. Don't copy half of it, because then I know that you copied it. Okay, so here's the, let me start off with the fundamental theorem of calculus. So what is calculus about? Suppose you have a function has a curve like that. And you want to find, let's call this x, and let's call the function little h of x. I don't want to use f or g because I've already used them for the homework problem. And you want to find the area under this curve between a and b. You want to find that area. Now, at first glance, you might think that that's not a very important problem. Who cares? But actually, it is, because when you see how you do this, you'll recognize that this relates slopes of things and integrals, derivatives and integrals, and that relates things like velocity and acceleration, and most of the laws of physics and engineering, the elementary stuff in mechanics and electrical engineering, are laws that have derivatives and integrals in them, and so it's important to understand what this is. So let's suppose you wanted to evaluate that. How could you do it? So one way to do it would be to say that you would calculate the area of a little strip, and then you would do that, that is, you would divide this thing into lots of little strips, and you would calculate the area of each strip, and then you would add them up. So that would be approximately correct, because each strip is a rectangle. You know its width, and the height is whatever the value of the curve is. So you just add those things up and you get the right answer. Well, it's approximately right. It's not exactly right because the strips don't exactly give you the area under the curve. The strips give you the area under a rectangle that's almost like the curve. So it's sort of obvious that if you took more and more strips and the strips were narrower and narrower, that the area that you would calculate would get closer and closer. And you can envision it in the limit as the width of each strip goes to 0. You can call the width of the strip delta x. And of course, the height of the curve is h of x for an x that lies in someplace in that little interval. So you could see that if you took the delta x's smaller and smaller, so there are more and more strips, but each strip had smaller and smaller width, less area, that in the limit you would get the exact answer. So you could do this, although it would be a mess. Now, in fact, that's the way your calculator does it. So when you give the calculator, when you tell the calculator that you want to calculate an integral, an area, and you give it the value of the function, that's the formula, you tell it what the variable is, you tell it what the limits are, and then it simply takes that interval that you give it, divides it up into little pieces, however many the calculator can handle, and calculates the area under each of them. Maybe it does it in 1,000 or 100, I don't know. And then it adds them up. So that's what a calculator does. And most people didn't use a calculator, and you would think that everybody would use a calculator. I mean, that's the easiest way to do things. Of course, you can use mathematical software, which would be even more accurate, just a fancier calculator, like Mathematica or Maple or something like that. Okay, now, the fundamental theorem of calculus says this. Suppose that I define area this way. I'm going to say, here's the function whose area I want to find, and the name of the variable is x, and so I'm going to represent, in a sense, the delta x by dx. This means that I've actually imagined that I've written this thing down, and I have a sum of delta x times h of x. So here's the h of x, here's the delta x. This is sort of a sum. And then what you do is you say, okay, now I'm going to let the delta x go to 0. So I'm going to take more and more strips until the width of the strip is 0. And then I'm going to add up more and more of these terms, and I'm going to take the limit. Now I'm going to define the area as this. So this is area between A and B. That's the definition of it. So now the question is, how do I evaluate this? Well, one way is just what I said, what a calculator does, or what you would do if it was important to get the answer and you didn't know any calculus. So you just draw a picture of it and estimate it. But now the fundamental theorem of calculus says, suppose that you have another function, h, capital H, whose derivative is little h. Okay, so suppose that that's true. Then, and this is the fundamental theorem of calculus, so now we have the equal sign here. Then, amazingly, what you do to evaluate this integral, to find out what that area is exactly, is you take this new function whose derivative is the function that you're trying to find the area of, and you plug in the upper limit, and you plug in the lower limit, and you subtract them, and you get the right answer. That's the fundamental theorem of calculus. Now, why this should work? Well, of course, you can prove it. In fact, that's what you're supposed to do in a freshman calculus course, but you don't have to memorize the proof. You're just supposed to understand the idea. Of course, this originates with Newton or Leibniz or some of those guys, and this is the fundamental theorem of calculus. Fundamental theorem of calculus. So it's surprising that if I want to find the area under a curve whose formula I know, all I have to do is find another formula, another function, whose slope is the one that that gives me the formula that I'm interested in, and then just evaluate that new function at the upper limit and the lower limit and subtract them, and I get the exact answer. So the fundamental theorem of calculus is that if I take this limit, that the end result will be this. So now I can say, okay, this means find the area under this curve between x equals a and x equals b, and the fundamental theorem of calculus says that if this is a nice function that is the derivative of something else, then one way to find the exact answer is to take that new function, evaluate it at the upper and lower limits, and subtract it. That's the fundamental theorem of calculus. Okay, now we want to apply that to the homework problem. So this makes sense so far? So you're all supposed to know this. Of course, I realize that most people don't. That's why I'm doing it in this course. Used to be that I assumed people knew it, and then when I actually used it in probability later on, people really got confused. Okay, so now one of the questions is, let's see. One of the questions is you have these two f's. Okay, so in case number one, you're given little f sub x of t. And it's equal to 0 if t is negative. It's equal to 1 if t lies between 0 and 1. And it's equal to 0 if t is greater than 1. And in case number two, you're given little f is equal to 0 when t is negative, and lambda e to the minus lambda t when t is not negative. Okay, so this is obviously like the world's simplest function, and this it'll turn out later is a very important one in probability. In fact, it's important in lots of engineering and science, the exponential function. Now you're asked to draw a picture of it. Okay. You want to draw the graph. So in this case, if that's t, and this is f of t, then, and this is 0 and this is 1, then the graph would look like this. It's 0 when t is negative, then it's 1 for t between 0 and 1, and then it's 0. That value is 1. So that would be what the graph looks like. Because you don't need to plot that graph, you can just draw it because it's only a constant. The difficulty here, in terms of the fundamental theorem of calculus, is that this function has 3 different branches. So it has a different formula here, then here, then here. So in other words, when you apply the fundamental theorem of calculus, you have to take that into account. You can't just plug in blindly because the function might not simply be a constant of 1 or be 0 throughout the whole range. It depends on what the range is. So you have to take into account that you have different branches. And in fact, in most real applications, that's what happens. If you're talking about mathematical formulas that are supposed to describe reality, it's reasonable that they should have a certain formula in a certain range and be 0 or something else in other ranges. So this is not just made up to make life difficult. That's in fact the kind of formulas that you find in reality. And we'll see later in the course that what this actually describes is it describes the randomness in the random number generator in a computer, among other things. Now this one, if I was to draw the graph of that, it would look something like this. And I did this in class, although you were supposed to actually graph it, not sketch it. So it's 0 for t negative. And then when t is 0, it is a discontinuity. It jumps from this branch to this branch and has the value lambda. And then if you plot the points, it'll look something like that. So in fact, that's another one of the observations here is that a lot of people really don't know how to draw a graph. So what you should do when you draw a graph, I'll go through this again later if we have time, put in the numbers. But what you should do is you should take various values of t, you plug them in, and you get to the formula, and you get the values of the function. And then you plot points that correspond to those, and then you connect them. So you have to be accurate in doing that, or else it's useless. Because what we're going to use this for later on in the course is we're going to compare theory and experiment. So the theory will be the smooth curve, the experiment will be some points. So you're going to draw the smooth curve, then you're going to put the points on the same graph. And if the points lie on the curve, that means that theory and experiment agree, which of course they should, certainly in this case, because these are examples that are made up to illustrate that. And if they don't agree, then that shows that there's some problem. So if you don't plot the thing exactly correctly, and you don't put the points on there exactly correctly, the whole thing is meaningless. So it's important to be able to plot a graph. Now, later, you can do it on your own scale. I made the scale this time, which means you can use software to do the plotting for you, which will give you perfect pictures. Of course, you have to know how to use the software, but that's up to you. I don't care. You're a computer scientist and engineer, so you can either do things by hand or not, depending on what you know. Okay, so those are the two formulas. And now we defined this G. So G is called a convolution. I'm going to leave out the subscript because it really doesn't matter. It's the same subscript in every case. Later on you'll see what this means. But for now it's just a calculus problem. And what it says is, take the function f, put them in here, and evaluate the integral. So you got to take this guy, put it in there, evaluate it, and then take this guy, put it in there, and evaluate it. And when you get all done, you're going to have an answer that's going to depend on t. That t right there, the answer is going to be a function of t, and then you're supposed to plot that function and observe it and make some calculations with it. So this is, in a sense, straightforward. Here's the formula. Here's the stuff that goes into the formula. Put it in there. Give me the answer. Okay. Now, it's important to recognize that this u here plays the same role as x over here. Is this x right here? I like to use t instead of x because I use x for a random variable name. So I put a t here. But if I'm going to put a t here, then, and that t is here, I have to use a different variable for the variable of integration. So I choose to use u. That's another thing that people seem to have problems with, is that if I give you a function and I give it in terms of t, then of course this defines it for all values of the variable. So if I call the variable u, then I put a u there, a u there, a u there, and a u there. If I call this variable t minus u, I put t minus u there, t minus u there, t minus u there, t minus u there. So you have to be able to understand that a function, you have what's called a dummy variable, and that dummy variable doesn't mean anything. You have to plug in, you can plug in any symbol you want, but you have to be consistent in using and interpreting the symbols throughout. Okay, so a lot of people, when they write integrals, for example, they just write stuff and they don't write the d part, because who needs it? Well, of course, if there's only one variable in here, you really don't need it. On the other hand, you shouldn't be sloppy. You should do mathematics the way you do programming. I mean, it's the same thing, except that if when you write a program and you're supposed to put something in there like a colon or a semicolon or a X or something and you don't, then it's not going to work. Whereas with mathematics, it'll work if the problem is simple enough, because then you're not actually using the formula. But if the problem is not simple enough and you write the wrong thing in there, it's going to give you the wrong answer. Like, for example, if I wanted to put this into a calculator and evaluate it, if I put in the formula and I don't tell the calculator whether or not the variable's name is u or t, it's not going to know how to do it. It has to know what is the variable of integration and what is the parameter. They're different. So it's important to put those things in. Okay, so let's do this. And let me do number 2 first. I'll do both of them in parallel. Okay, one of the questions was we want to calculate the integral between a and b of this f dt. Okay, so this means find the area under this curve between a and b. So I can use calculus or not, depending on what I need. So let's look at the first case. In the first case, here's the function. So this is 0, this is 1, that's 1. And in the first case, in our case, a is equal to, let's see, what do we take it to be? 0.25, and b is 1.35. So that means I want to find the area under this curve between 0.25 and 1.35, which is obviously this area right here. If I want to be careful about it, that says that I'm going to take this integral from 0.25 to 1, and in that range, the value of the function is 1. And then I need the remainder of the area, which is between 1 and 1.35, and in that range, the value of the function is 0. This part is obviously 0, and when I'm left here now, I can do this 2 ways. One is I can say, okay, I'm going to apply the fundamental theorem of calculus. That means I have to find the function of t whose derivative is 1. Well, that's obviously t. So this thing right here, when I integrate it, I get t because the derivative of t is 1. And then the notation says plug in the lower value and the upper value and subtract them. That's what that bracket means. So that means this would be t evaluated at 1 is 1. T evaluated at 0.25 is 0.25, and the difference is 0.75. So that's the answer. But now you didn't need calculus to do that, because if you look at this right here and you say, what does this mean? This means the area under this curve. Well, because the curve is a simple geometric figure, I can simply calculate it by saying, well, it's a rectangle. The width is 0.75, the height is 1, so the area is 0.75. So I didn't need calculus in order to evaluate it. Okay. But the second one, I do need calculus. So the second one, you want to evaluate the area from 0.25 to 1.35 of, I'll write it first as lambda e to the minus lambda t dt. Of course, in your case, lambda is 2. But I'm going to leave it as lambda. In fact, I think what I'll do originally is I won't even put in these values here. I'll just call them a and b, so you can see exactly what's going on. All right, so what I have to do is I have to find the area under a curve which looks like this. When the values are a and b, here's a and here's b. In our case, it's 0.25 and 1.35. So now I can't find that area by geometry. Although if I gave it to a calculator and I told the calculator what the formula is and what the variable is and what the limits are, it would simply calculate the area by dividing this up into little strips and adding them up. And as long as it can do that into enough tiny strips, it'll be sufficiently accurate. So that's what a calculator does. And now, as I said, if I had a choice, I would rather buy a calculator, TI-89 or 93 or something like that, or HP or something that does a scientific calculator that will evaluate integrals, rather than buy the textbook. Textbook you'll use, and then at the end of the course you sell it. Whereas maybe you don't even use it. Whereas a calculator, you should be using your whole life if you're a scientist or engineer. Okay, anyhow, I could evaluate this thing numerically, or I could evaluate using the fundamental theorem of calculus. Now, almost everybody who did it used the fundamental theorem of calculus. It's easy in this case. What you do is you find a function whose derivative is that. Well, obviously, if I differentiate e to the minus e to the minus lambda t, I will get this integrand right here. And then I have to evaluate that at a and b and subtract them. Okay, now in our particular case, the lambda is equal to 2, the a is equal to 0.25, the b is equal to 1.35. So this would be e to the minus 2 times 0.25. That's the lower one. I'm switching them around because when I subtract, the minus sign cancels. And then the other one would be e to the minus 2 times 1.35. Of course, you have to know how to evaluate e to the something. A lot of people didn't know how to do that, apparently, because the calculator will do that for you also. And when you get done, that answer will be, according to this, that answer is 0.539. 0.539, at least to 3 decimal places. Okay, so the area under this curve, when lambda is 2, between 0.25 and 1.35 is 0.539. Okay, any questions about that? So here I had to use the fundamental theorem of calculus, but it was easy because it's easy to see that the derivative of that is that. However, the thing that's difficult in freshman calculus often is that the emphasis is on finding the function whose derivative is the integrand, which involves lots of tricks rather than the essence. And the essence is it doesn't matter how tricky it is, the idea is the same in every case. Okay, so the trouble is people get bogged down with the tricks of integration, and then they forget those tricks, but those tricks are pretty much irrelevant. And in reality, most of the functions that you have to integrate are simple anyhow, so you don't even need those tricks. But if you understand what you're doing, it doesn't matter because you can always go back and look the tricks up. But if you don't understand what you're doing, then you can never solve a problem that you haven't already solved before. Okay, so any questions about this? Okay, so now let's look at the convolution. So one of these I did in class. I did this one in class. Okay, now let me just write that out again so you can see what's going on. Okay, so we know that g of t is given by this integral between minus and plus infinity, and we take this function, we evaluate it at u, and we evaluate it at t minus u, and then we find the area under the curve that results when we multiply these two things together. So what I'm going to do is I'm going to put in what this function is. Okay, so first of all, what's f of u? Well, it's lambda e to the minus lambda u, but it's lambda e to the minus lambda u, according to the formula here, only if the u, all right, and I have to replace the t here by u, only if this u is greater than 0. So since the integral runs from minus infinity to plus infinity, for all the values of u between minus infinity and 0, the function is not that, it's 0. So in effect, what I do is I start the evaluation of 0, because all the area to the left of 0 is 0 because the integrand is 0. Okay, let me worry about the upper limit now. Now let's put in the other part, f of t minus u. This is lambda e to the minus lambda t minus u. And then I have my du. Now, we know that the t, well, let's see, first of all, suppose that t is negative. If t is negative, then we already know that this is going to be 0. So let's not worry about that for the moment. That's easy. Suppose t is not negative. If t is not negative, then what happens is that when u runs from 0 to infinity, when u reaches the value t, that this thing in parentheses, this argument, is going to become negative. And if it becomes negative, then according to the definition of the formula, you jump from this branch, which is for the argument not negative, to this branch when the formula or the argument is negative. So that means that as u runs from 0 to infinity, when u reaches t, the piece that's in here is replaced by 0, which means that everything that remains, the integral becomes 0, the integrand becomes 0, so the area is 0. So therefore, the upper limit is really t. And now it's just a matter of doing the arithmetic. Okay, so now I look at what's in there and I just do some algebra. So I have the integral from 0 to t. Lambda times lambda is lambda squared. Then I have e to the minus lambda u. Then I take this and I simplify it. So that gives me e to the minus lambda t times e to the plus lambda u. And I still have du. So this is just algebraic simplification of the integrand. And then I realize, well, this is a constant. And e to the minus lambda u times e to the plus lambda u equals 1. So the u cancels out. Okay, so that makes it nice and easy. And all that's left inside then, I'll just write it, cancel it like that. All that's left inside is a constant and e to the minus lambda t. But remember, I'm integrating with respect to u, so therefore t is a constant as far as the integration is concerned. So therefore I can take all the stuff inside the integral sign out. This is the rules that you learn about calculus when you take freshman calculus. So if I want to find this area, obviously if I have an area and it's multiplied by a constant, that just means I can take that constant outside and look at the area of 1. So I'll take the constant outside. So I have lambda squared e to the minus lambda t, and what's left is the integral from 0 to t of 1 du. All right, so now all I have to do is evaluate this. Of course, I don't need calculus to evaluate that. It just says find the area under a constant. So if the area under a constant between 0 and t is obviously t. But if I want to use the fundamental theorem of calculus, then I can take this guy here and I can say, find the function of u whose derivative is 1. Well, it's u. Plug in 0 and t and subtract, so that gives me t minus 0, or t. So that's this part right here. So the answer is lambda squared t e to the minus lambda t. But this assumed here that the t was greater than or equal to 0. If the t was not greater than or equal to 0, then this integral would be 0. So the answer in this case is that the integral is equal to 0 if the t is negative. And I got to keep stressing, you have to have the function defined everywhere. So if it's negative, you got to write down the answer. Don't just leave it out, because if you do, then of course you're not going to get the right answer when you plug into other formulas. The other part is lambda squared t e to the minus lambda t. Because I did this in class. Probably doesn't hurt to do it again. Okay, then it asks you to find, well, okay, that would be the answer to g of t for the second case. So before I do the first case, let me integrate this. So any questions up to this point? Yeah.
How did you get an upper limit of t?
This one right here?
Yeah.
Okay. I did it slightly differently from what I did in class, but I sort of skipped a step, but I thought I could at this stage. Okay, here's what I'm arguing. I'm going to take these functions, I'm going to put them in here. So there they are. But these functions are given by those formulas only when this is not negative and when t minus u is not negative. Because remember the definition. The function is 0 if its argument is 0, and the function is this formula if the argument is not 0. So for this case, I just take this formula and replace t by u. For this case, I take this formula and I replace t by t minus u. Now, the u is going to vary between minus and plus infinity. When the u is negative, when it's less than 0, this formula is not given by that, but it's given by that, by 0. So instead of writing everything out, I can do this in my head. I can say, okay, when u is negative, then I replace this by 0, which means that the integral is 0 plus the remainder starting at 0. So I immediately just get rid of the lower limit and say it starts at 0. So that takes care of this. And I'm assuming here that, for the moment, that the t itself is positive. Okay, so now what about this piece here? Now, the u, this u, is going to vary from 0 on up. If t is positive, then t minus u is positive, and that means that the branch that I use is the one with this formula right here. But as u gets bigger and bigger, it's going between 0 and infinity. As u gets bigger and bigger, eventually it reaches the value t, and then when it exceeds t, this thing in parentheses, this argument, becomes negative. When the argument becomes negative, according to this formula, if I replaced t by t minus u, this thing would be 0 if t minus u were negative. Okay, so when u reaches t, this becomes negative, so this part of the formula is replaced by 0. If it's 0 from then on, that means that the integral stops at t. So this t is cut off because of this, just like this one was cut off because of that. So it's only when u is between 0 and t that both of the pieces inside are not 0. If either one of them is 0, then the integral is 0. So the first thing I do is I look at the integral and I cut off all the parts where the integrand is 0. Okay? Then the rest of it is simply arithmetic. It's easy. Okay? So the essence of it is right here. But the important thing is you have to recognize what this notation means. This is like an algorithm. And the trouble is, I guess, in freshman calculus is that all the integrals simply have only the t in them, and they don't have functions that have 2 different pieces or 3 different pieces in the formula. But for practical applications, in fact, that's the usual case. And for this application, it's obviously the case. And we'll see later that this is a real application. It's not just a formula that I'm making up for no reason at all. Okay, so once you understand that this becomes this, and then the rest of it is simple because everything just factors out and all you're left with is a constant, and that gives you this is the answer, that's all there is to it. Okay, now another question here was to evaluate or find the area under this curve. So let me erase this right here. Here the question is, find the area between A and B of g of t dt. So I want to take this answer and I want to put it in there. Now, this works for all t greater than or equal to 0. So that means in our case, since A is 0.25 and B is 1.35, all I got to do is take that and put it in there. Now, if I want to evaluate this numerically, I have to have a value for lambda. I said take lambda equal to 2. So that would make this 4t e to the minus 2t dt. Now you can evaluate this by integrating by parts, but that's more trouble than it's worth. It's not necessary. This is just a function whose area you want to find. If I were to draw the graph of that, which is one of the questions that was asked, the graph would look like this. Here's g of t. Here's t, 0 for t negative, and then the graph would look like this. And a lot of people didn't draw this graph very well. Remember what you're supposed to do. You take values of t, you put them into this formula, then find the value of g of t, and you write some points, and then you connect the curve. Of course, you're supposed to do it for an infinite number of points. That is, you have a smooth curve, but you can't really do that, so you just do for some representative points, and you connect the curve. And then this thing says find the area under that curve between 0.25 and 1.35. But now you can't do this by geometry, so you have to use calculus. So there are 2 ways. One is to use the fundamental theorem of calculus, but that means I have to find a function whose derivative is that. Well, I have to integrate by parts or use some trick, so that's really not important. I mean, you're supposed to know what you're doing, but the actual tricks of integration are pretty much irrelevant. The way to do this is to plug into your calculator this formula, tell it the name of the variable, tell it the upper limit, the lower limit, and press the button. And then the calculator will essentially calculate the area by dividing this up into strips and adding them up. And if you do that, the answer will turn out to be 0.661. Okay, that's the answer. Any questions about this? So this is easy from my point of view, because remember, I did all this in class. So all you had to do at this stage is put this in the calculator and press a button. Like, I don't know, 4 seconds, 5 seconds. Not a lot. So everybody should know how to do that. Okay, this will turn out later to represent the probability that a random variable of a certain type takes a value that lies in this range. So 66% of the time, that random variable will lie between that number and that number. That's what it will mean later on in the course. Okay, so now we got to do it for the case, the hard case, the case that I didn't do, which is I want to evaluate that for that. Any questions so far? Okay. All right, so now we're going to take a case where let me write it as f of y, because I don't want to use t or u, just be as simple as possible. So f of y is equal to 0 if y is negative. It's equal to 1 if y lies between 0 and 1. And it's equal to 0 if y is greater than 1. This is like the world's simplest function. It's either 0 or 1. And when I put it in this integral, the only time this integral is not going to be 0 is when the integrand is not 0, which means that neither this nor that has the value 0. They both have to be 1. And when they are both 1, then the integrand is 1. And when any one of them is 0, the integrand is 0. That's all there is to it. Okay, so how do I do that? The first thing to say is this. Now, this guy here, if I went over to this formula and replaced y by u, I would see that this thing is 1 only if y, or in this case u, lies between 0 and 1. So I can immediately see that this is the same thing as the integral between 0 and 1 of 1 times f of t minus u du. And so now the question is, I have to find the area under this curve when u varies between 0 and 1. Now what is that? Well, that picture, that curve, looks just like this. It's just a box. The only thing is you don't know where it's located, because where it's located depends on the particular value of t. So in fact, you could draw a picture of it like this. Here is u, and here is f of t minus u. Because u is the variable, t is just a parameter, and I want to find the area under this curve when u runs between 0 and 1. So what is the picture of this curve? Well, the only time that this thing that fits in here is not 0 is when t minus u lies between 0 and 1. So you can see that if u is equal to t, or u is equal to t minus 1, then between those two limits, this thing is going to have the value 1. And everywhere else it's going to be 0. Right? There's a width of 1, a window of size 1, in which this function is 1, and every place else it's 0. So if I plugged in u is equal to t, that would give me f of t minus t, or f of 0, and as u got bigger, I would be outside the interval. If I plugged in u is equal to t minus 1, this would be f of 1, and then as u gets bigger, I would be outside the interval. So you want to see that this graph is exactly this. That's all there is to it. What I want to do now is I want to find the area under this curve between there and there. Now, excuse me, I want to find the area under this curve between 0 and 1. So the question then is, what's the value of t? because different values of t are going to take that picture and they're going to move it to different places. Okay, so suppose, for example, let's start off, and let's say that t is negative. So here is t, here is t minus 1, and here's 0, and here's 1. So the graph is here. This is supposed to be 1. And I'm finding the area under this curve as u varies between there and there. So as u varies between here and here, there is no area because the box is over here. So right away I know that the enclosed area is 0 if t is negative. Okay? Now, similarly, let's see, what I think I'll do is I'll erase, I'm running out of space here. All right, let me go over here. Let's look at the same box. Okay, I'm going to erase this here, move this over here. So here's the same graph. Here's 0, here's 1. But now, instead of t being negative, I'm going to let t lie between 0 and 1. So there's t, and there is t minus 1. So now the box looks like this. And we want to find the area under this box between 0 and 1. That's that area right there. So what is that? Well, the height is 1, the width is t, so that area is t if t lies between 0 and 1. And notice that the way I'm doing this is I'm not even using calculus. A high school student could do this if I simply said to him, okay, this is the function right here, and this symbol means find area. That's all I got to say. Now, since the function is only either 0 or 1, you don't need any calculus. You don't need the fundamental theorem of calculus because all the areas are simply rectangles. So, this area between here and here is obviously t. Suppose that, draw another picture. Let me erase this one and go back over here. Suppose now, here's 0, here's 1. Suppose that t lies between 1 and 2. So there's t. That means that 1 minus t lies between 0 and 1. Excuse me, t minus 1 lies between 0 and 1. I want to find the area under this curve between 0 and 1, which is the area under that rectangle between t minus 1 and 1. What is that area? Well, its height is 1, its width is 1 minus quantity t minus 1, or 2 minus t. So the area of this rectangle is 2 minus t. So that answer is 2 minus t as long as t lies between 1 and 2. But suppose now that t were greater than 2. So if t is over here, then t minus 1 is greater than 1. And just like this case, the box is outside of the interval between 0 and 1. Okay? The box lies between t minus 1 and t. So I should redraw this really. Let me do that. Okay, so we're looking at this picture right here. There's the t minus 1. Here's the t. But now, t minus 1 is bigger than 1 because t is bigger than 2. So if t is bigger than 2, that's 2, then 1 lies over here, and that means that the box is here, and I want to integrate over here, so the answer is 0. In other words, this is 0 for the same reason that that's 0. In this case, the whole box is to the left of 0. In this case, the whole box is to the right of 1. And in this case, the box overlaps. So that's my answer. Now, if you draw the graph of that, the graph would look like this. Well, let's see. We want to draw the graph of g of t. So there's g of t. Here's t. If t is negative, it's 0. Here's the value 1. Here's the value 2. Between 0 and 1, the graph is t. Between 1 and 2, the graph is 2 minus t. Greater than 2, the graph is 0. That height right there is 1. There's your graph. I did that whole thing without any calculus. All I had to know was that integral means area, and I had to understand what a function was. And then I took the function, and I saw that it's a box, and the only thing that's going to affect the area between 0 and 1 is where the box is located. So if the box is outside the interval between 0 and 1, as is here and here, then the answer is 0. If it overlaps, then it depends whether it overlaps this way or this way. But in either case, the area is simply a rectangle whose width is t and whose height is 1. So there you are. That's the answer. Now, I could do this by calculus, so let me do it that way. But the point I want to make is that you didn't need any calculus. If you understand what calculus is, then you know that all I'm asking you to do is find the area under this curve where this function is the world's simplest possible function, simply a constant in the interval between 0 and 1. So everybody should get this right. I mean, I know that never happens. Most people get it wrong. But my view is you're a scientist or engineer or that far from it because you're going to graduate soon. And you've all taken calculus, and this is the only thing you have to do, and you have 3 weeks to do it, and you can ask anybody in the world how to do it. You would think everybody would get it right. I don't understand how you could not, but that's what happens. Okay, let's say that you have no idea what you're doing, but you paid attention in calculus class. So what do? Now you just do it mechanically. Okay. So what you learn to do in calculus is if you have a complicated argument here, you make a substitution. So for example, what I'll do is I'll say, let t minus u equal y. Let t minus u equal y. So this becomes the integral. The 1 is not affected. And this is going to become f of y. So that's simpler. But now what about the rest of the stuff? Well, what is du? Well, according to this, if I use the rules of calculus, then I would find that dt, or let me write it this way, d of t minus u is equal to dy. But t is a constant, so I get minus du equals dy. So I replace du by minus dy. That is, minus du equals dy, du equals minus dy. Okay, so I replace du by minus dy. Now, why you can take the minus sign and do all this kind of stuff, those are the things you learn in algebra and calculus throughout your whole life. Nobody really thinks about those things, although I keep emphasizing that you can make these manipulations because, without thinking about it, because familiarity breeds contempt. But there's really quite a bit here. But the rules of mathematics just say, just follow these rules, and if you follow the rules, you'll live a happy life. Boring, but happy. Okay, so now what about the limits? Well, I see that when u is equal to 0, then y must be equal to t. Okay, because t minus u equals y. So if I replace u by 0, I have to replace y by t. When u is equal to 1, then I must replace y by t minus 1. Then I use the fact that instead of integrating from t to t minus 1, I'll integrate from t minus 1 to t and change the sign. And so now all I have to do is evaluate this. Well, now we're back to the same problem as before. Actually, it's easier. Let me do this here. Here's y. Here is f of y. And f of y is 1 when y lies between 0 and 1, and 0 everywhere else. So there's f of y. Now what I want to do is I want to find the area under this between t minus 1 and t. So I have a window of width 1 between t minus 1 and t. But the answer is, well, that depends on where t is. If t is negative, then t minus 1 lies over here, and the enclosed area is 0. If t lies between 0 and 1, then t minus 1 is there, and the enclosed area is t. If t lies between 1 and 2, then t is there, t minus 1 is there, and the enclosed area is 2 minus 2. And if t lies bigger than 2, then t minus 1 is bigger than 1, and the enclosed area is 0. Now, of course, I could just draw this diagram, and when I'm integrating, since that's finding an area, I could simply integrate this by finding the function whose derivative is 1, which of course is y, and then plug in the upper limit and the lower limit. Get the same answer. But again, here I've used calculus formally in order to change the variable to change that to that. And then after that, it's the same problem as before. So this is easier because you're just plugging something in. I mean, where I left it for you was I gave you this. So to go from there to there, I don't know, about a minute. Of course, if you don't know that, that's calculus, then you have to do it the way I did it earlier, which would take a little bit longer, but still is something you should be able to figure out. It's not something that you memorize. So, any questions about that? So with hindsight now, this is really easy, right? I mean, you could do. High school student could do this. Only fact you have to know is integral sign means area, and the definition of the function is whatever it is, which is the world's simplest function. That's all there is to it. The rest of it is just following the rules, just doing what it says. Take the area under this curve when the curve is defined by that function. That's it. And that function is either 0 or 1. So all you have to do is figure out where it's 0, where it's 1. That's all there is to it. And if the function is 0, then the area is 0. If the function is 1, then the area is the area of the rectangle that is enclosed between 0 and 1. So the important thing about calculus, the important thing about all mathematics, in my opinion, is not facts, it's reasoning. You have to be able to reason in a rational scientific way. And the reasoning behind this is no different than the reasoning in programming. I mean, the syntax is different, but the concepts are, it seems to me, exactly the same. All you have to do is understand what your definitions are, what the rules are, and then you manipulate things according to those rules and definitions. Okay, now we still have one more piece. We have to find the area under this curve. So let me erase, I'll do it here. The question now is, here's my G for this case. Here is 0, 1, 2, and the graph looks like this. So this curve, the formula for that straight line is simply t, and the formula for this straight line is 2 minus t. And I want to find the area under that between 0.25 and 1.35. So the integral from 0.25 to 1.35 of g of t dt, which would turn out now, in probability terms, if I took the random number generator and spun it twice and added the two values up, like I was playing dice with a random number generator, and then said, what's the probability that the result, the sum of those two values lies between 0.25 and 1.35, the answer would be whatever this integral is. You don't know why that is, that's what's going to come later in the course. Okay, now, what is this? Well, I could write this as the integral from 0.25 to 1 of t dt. I have to break this up into its pieces. So between 0.25 and 1, the integrand is t. And then between 1 and 1.35, the answer is, or the integrand is 2 minus 2. And then I just have to evaluate that. Because these are like really simple integrals using the fundamental theorem of calculus. These are as easy as they come. But you don't even have to do that because this is a simple geometric figure. So the simplest way to do that is to recognize that I'm trying to find this area right here. The trapezoid or something like that. I don't know what that is. I forget. But I don't have to remember it, see? It's like doing mathematics is like, and knowing things is like knowing how a telephone works. You don't have to remember every telephone number. All you got to remember is telephone book, alphabetical order, and that's all there is. And every number is there. Okay? So you don't have to remember anything, just remember. Area, function, okay. What did you figure out? Okay, so how do I find this area here using ordinary arithmetic? Well, let's see. The total area of this triangle is 1, because the area of a triangle is, well, let's see, I could simply take this thing and switch it over to there like that, and then I would have a rectangle, or a square, whose area is 1. Its width is 1, its height is 1. So what I'll do is I'll take the area of the total triangle, which is 1, and subtract the area of that triangle and that triangle. Because each of those is a right triangle, so each of its areas is half the area of the square. So the area of this triangle here is 1/2 times the width times the height. Well, this line is at a 45-degree angle, so the width and height are the same. I guess this is what is called an isosceles triangle. I think, is that right? Right triangle?
Right triangle.
What is it? It is a right triangle, but it's a right triangle in which the two sides off the hypotenuse are equal. They're both equal to 0.25. So this area is minus 1/2, 0.25 squared. That's the area of this triangle. This triangle is the same. Its area is 1/2, and the width is 2 minus 1.35, which is 0.65, and the height is 0.65, so it's 0.65 squared. So now you just put that in your calculator, and that value will turn out to be exactly, this is 1 minus 0.2425, or in other words, equal to 0.7575. Now the fact that the area for the triangle turned out to be 0.7575, and the area for the square in the earlier problem turned out to be 0.75, that's just a coincidence. That's just because of the particular values of A and B. So I didn't know how that would turn out before I made the calculation. Okay, so that's the answer. Now the other thing is drawing the graphs. And the way to draw graphs is, here's an example of one that was done just right. And this person drew the graphs this way, made a table like this. I'll do this here. T. And this is for the second case, because you don't need any calculations in order to draw the graphs when the graphs are all rectangles or triangles. But in the case in which they weren't, this is the second case, what this person did is wrote a T, here's little f of T, here's big F of T, and here is G of T. And then she took the values of T as being 0, 0.2, 0.4, 0.6, and so forth, and you just plugged in the numbers. That would be 2, that would be 0, that would be 0. This would be 1.34, this would be 0.33, this would be 0.54. And then next one for 0.4, the answers are 0.90, 0.55, and 0.72. And so on. And so, in each case, what you do is you take the values of T, and here's the value of f of T, you plot the points, and then you draw a smooth curve between them. So that was it. So basically, this problem is sort of a review of the essence of calculus, at least as I see it, plus it uses results which we're actually going to use later or it produces results which we're actually going to use later on in the course. And At that time, then, we won't have to worry about how they were derived. We'll just say, well, what we're doing then is we're taking a convolution of two functions, and then if we did it, this would be what we would get. That's the way I'm going to do it. So you don't have to actually take the convolution, because we will already have done it. All we have to do is understand what convolution means and why it has a probability interpretation. Okay, so are there any questions about that? This actually took longer than I thought because I wanted to go over the sample test. Because I can do that next time. I can start it now. I've got about 5 minutes left. Any questions about this? Or comments? Yeah.
Why weren't you my calculus teacher?
I don't know. I am. Actually, the way life works when you take courses is you always learn the course the next time you use it. You never learn calculus until you use calculus. So in this course, you're going to learn calculus because you're actually applying the stuff that presumably you learned before but didn't really get. Of course, you're supposed to be learning probability, but unless you take another probability course, this will have no effect. It just prepares you for the next one. What you want to do is you want to take another probability course. You don't want to take this one again. That's the important viewpoint. Okay, for the take-home exam, or the homework, not the homework, what am I talking? The midterm. Where do I have that? Okay, let me just read the problem, do the first one or two, and then I'll do the rest later. This should be easy also. Of course, you can always say that after the fact. So you consider two identical looking coins. C1 is a fair coin, C2 is biased. And it's biased, that means that the probabilities are not all equally likely for each face. And it says that it's biased such that the probability of head on any toss is 3/4, so the probability of tail would then be 1/4. And question 1 says, suppose that C1 and C2 are tossed together, find the probability that they match. Okay, so I'll go over this next time, but there's a start. This is the way these things work. So let's call it P1. Let the probability they're going to match. So that's equal to the probability how can they match. Well, you could get HH, or you could get TT. Simpler way to do it. Okay, now what's the probability of HH? Well, we have to make an assumption here. The reasonable assumption is that the coins are independent. In other words, there's no reason why the outcome of one coin should have any, knowing what one coin is, should give you any information about what the other coin is. So if we make that assumption, that means the probabilities are P, let me call it H1 and H2, T1 and T2. So it's a probability that coin 1 is ahead times the probability that coin 2 is ahead, plus the probability that coin 1 is a tail times the probability that coin 2 is a tail. Now this, of course, is the important step in recognizing that in order to be able to solve the problem, you have to make an assumption. The only reasonable assumption is that the coins are independent. But nobody has ever taken a problem like this after the quiz and complained to me that I didn't say whether or not the coins were independent, so they didn't know what to do, so that was the reason they didn't write the answer. As soon as you realize that that's, in fact, what most people do is they never even think about it. It's sort of second nature. Okay, now, coin 1 is the fair coin, right? So the probability that you get a head is 1/2. What's the probability of head on the second coin? Well, it's 3/4. Similarly, what's the probability of tail on the first coin? 1/2. What's the probability of tail on the second coin? It's 1/4. And that answer then is 1/2. Now there's another way to look at it. For example, I could have looked at this as actually being the theorem of total probability, because I could say, well, I have a partition in my sample space. Coin number 1 is either head or tail. And then I multiply that probability by the conditional probability that coin number 2 is head or tail. But if the coins are independent, the conditional probability is the same as the unconditional probability, so I get the same answer. But if I'm really smart, I don't even have to do this. I could look at it and I could say, okay, I got a fair coin and a biased coin. Now, the biased coin is going to give me something, but it doesn't make any difference what it is. The 3/4 and the 1/4 are irrelevant. I could make this P and this Q as long as P plus Q adds up to 1. Because whatever the second coin is, the first coin has a 50-50 chance of being what the second coin is. Because the first coin is unbiased. So no matter what I got, whether I got a head or I got a tail on the second coin, the probability that the first coin is a head is a half. The probability the first coin is a tail is a half. So the probability is not affected by what the second coin is. So I could immediately have written down the answer as being 1/2. Okay? Of course, what you should do now in probability is, suppose you know nothing except the fact that you're talking about probability. So this is like the second easiest course in the world. Okay? Because probabilities all lie between 0 and 1. So if they all lie between 0 and 1 and you don't know what the answer is, well, guess a half. It's right in the middle. How far off can you be? The only course that's easier than this is logic design, where all of the answers are either 0 or 1. You don't even have to worry about the ones in the middle. Okay, so next time I'll finish this exam and you should have your questions ready, and then on Thursday we give the exam, which will be basically the same as the sample.
Can I get a copy of the